So thanks everyone for coming. Today I want to talk about a library that me and Julian have been working on for the last little while called DistributedNext. I'll start with a little introduction. Let me page down. Right, there we go. Okay, so I work at a research facility called the European X-File. We basically operate a giant laser and scientists use it to do experiments. And my job is to help the scientists convert the data that we record into something that's scientifically meaningful. And Julian, well, you already saw Julian's talk. He works on Dagger and AMD GPU.jl and like a million other things. We originally met when we were both working on Dagger. And along the way, we started discussing distributed computing and that kind of thing. And that's how I got involved with Distributed. So for those of you who, yeah, that's right. So for those of you who are unfamiliar with it, distributed.jl is one of Julia's standard libraries, and it's designed to do distributed computing. It's based entirely on RPC calls, so remote procedure calls. And the idea is that if you add a worker, then you can then make some arbitrary call on that worker and have the result returned to you. So it's kind of like it exposes a very functional interface. You can call arbitrary functions and get the results. This is quite convenient, but it also means that distributed requires that each worker has its own, has the same state. And it's kind of old as well. I don't know the exact date when it was created, but it's been around from nearly the beginning of Julia. I want to say something like 2012 or 2013. There's a little demo up there of what the API looks like. And distributed has some limitations. So Julian already spoke about the thread safety one before. An issue was opened for this lack of thread safety like 4 or 5 years ago, back in 2020. And the actual fix for that thread safety issue wasn't like horrendously complicated. There was a PR that was merged fairly quickly. However, every time it was merged, there would be hangs in CI. And distributed is used for running the tests of Julia itself. So if those tests hang, that's kind of a disaster for the whole language, because then development will basically stall because you don't know if it's distributed causing the hang or your PR is causing the hang. And so out of caution, this PR got reverted, and I think it was merged and then reverted like 2 or 3 times until finally, this year we finally got it over the line. So in Julia 1.12, distributed will finally be thread safe. Yeah, well, that doesn't display very well, but there we go. Distributed will finally be thread safe. But you know, that problem wasn't solved back when we started thinking about DistributedNext, and so this was one of the issues we had. Another issue is poor communication performance. So like I said, distributed is based on remote procedure calls. It does have abstractions. It does have one abstraction called a remote channel. And naively, you might think, or at least I thought, that maybe a remote channel would have like some kind of optimized implementation, since you're only doing like a limited number of things. It doesn't. It's actually like every operation on a remote channel is also based on remote procedure calls. And last night I did some little benchmarks of the performance. And you can see that for a local channel, we get something on the tens of nanoseconds, which is not too bad. For a remote channel that's on the same process, the performance is not too bad. Like, it's a couple times worse, but there's still 0 allocation, so yeah, not too bad. But as soon as you go to a different node, it's like 1,500 times slower, which is a little unfortunate. Now, admittedly, some of that overhead is probably coming from network traffic, but still, 1,500 is, you know, quite a big factor, and I'm sure that there are things we can do to improve this. You'll also notice that we have a lot more allocations now once we go to a remote node. Another issue is the development pace of distributed. So like I said, distributed is a standard library. And oh my God, I'm running out of time. It's a standard library, and so the barrier of entry is kind of high because it has to be somewhat high quality. The people who can review distributed PRs are very busy, like horrendously busy. And distributed itself is not particularly easy to get to grips with. It's not that the library is bad designed or anything. Distributed computing is just a hard problem. And so the end result is that PRs are kind of slow to get merged, and the development process is quite slow. And so Julie and I decided a little while ago to try making a soft fork of distributed called DistributedNext. This is, it's a soft fork. And the idea is to make it a separate package so that we can play around with some ideas for improvements to distributed that might actually get upstreamed in the future. What else do I have up there? I also took the opportunity to clean up the code base a little bit, which should make development a bit easier. DistributedNext shares the same API as distributed for now. And so if you want to support both distributed and DistributedNext, you can do that fairly easily. This is what Dagger does, for example. Basically, you can set up a preferences system and load either one or the other depending on the preference. If you do this, just keep in mind that distributed and DistributedNext are completely independent modules, so you can only use one at a time. You can't remote call a distributed worker from the DistributedNext function. Okay, that's not going to work. And I quickly want to go over some improvements. There've been a whole slew of bug fixes we've made to DistributedNext. Some of those we've also upstreamed to distributed. This is actually also why the thread safety support in distributed.jl was merged in time for 1.12. Along the way in CI, we came across a ton of hangs in DistributedNext, and we managed to track those down to some lingering tasks. Those were fixed, we upstreamed them to distributed, and now we finally get thread safety, which is extremely cool. One of the cooler features is that DistributedNext will try to automatically figure out which is the fastest interface on your machine if you have a Linux system. And so if there's if you're on a compute cluster and you have a control network versus InfiniBand, it will automatically try and pick the InfiniBand network now. I'm probably running out of time, so I might go very quickly through these.
You have time. We can
I have time?
shrink the next bit a little bit.
Okay, cool. There are some plans that we have for the future of DistributedNext, and we're also very open to your ideas as well. One of them that we've come up with is some optimized implementation for remote channels. So you saw before that there was a 1,500 times performance hit from communicating to a remote node. And here's an example of an alternative implementation that could be type stable and have zero allocations. So the idea is that instead of relying on RPC calls for operating with remote channels, we could actually set up a separate I/O with its own interface and port for each channel, and then we could spawn a separate loop for this channel. This would be specialized on the element type of the remote channel, and the idea is that this should provide a much faster implementation than what we have now. That's one option. Another thing that we're discussing, oops. Okay, that's not right. Let me see. Okay. Another thing we're actually working on at the moment is support for worker state callbacks. So sometimes when you're working with a bunch of workers and you're adding and removing them or something, you want to get some kind of notification or have some operation happen whenever they are brought up or brought down. This is what worker state callbacks are for. This is just hanging around in a PR that I should finish soon. And I remember now, I actually skipped over a slide, I think. Yes, I did. If you haven't seen it before, there is a library called parallelprocessingtools.jl, which was developed by Oliver Schultz. It's really cool, and it has this awesome macro in there called always everywhere. The idea is that you can put all of your imports and like your module loading stuff into this macro, and every time a worker is added, it will automatically run this, which is great because you don't have to ensure that all of that code is executed every time you add a new worker. This is like an awesome quality of life thing. Okay, I will move on. Another thing that we were thinking about is having better support for workers on different clusters. So imagine that you have like one worker on your laptop, then you've got some other workers on your compute cluster, and maybe another worker on your desktop. If you're SSHing to your compute cluster, let's say that the worker on your desktop wants to talk to the compute cluster worker. Well, right now, I'm not sure that would work because they would need to talk directly to each other, and maybe that wouldn't work because of the SSH connection or whatever. The idea is that maybe we can figure this out automatically and route all the communication through your laptop so that this is all seamless. That's just some of them. We do have some other ideas, which are over there. So a big one would be having type-stable interfaces and custom serialization. For those who are unaware, the serialization library in Julia is intentionally type unstable. So it has like these @ no specialized macros everywhere. And that causes allocations and GC problems and so on. There might be a way to add interfaces that are more type stable so we could improve performance there. Another one is observability tools, so like monitoring how much traffic is being transferred through workers and that sort of thing. A big one is actually cancellation. And here I actually have a question for you guys. Has anyone used distributed.interrupt? One guy. Okay, good to know. So I actually only learned about this function today. It apparently allows you to cancel long-running jobs. But anyway, we basically want to add better support for cancellation throughout distributed so that if you have like a remote call that's taking like a minute or something, you can safely cancel it and be somewhat confident that it won't break everything if you just hit Control-C. And if you have things that you would like to have in DistributedNext, we would also like to hear that. So in summary, we are working on DistributedNext to fix like bugs and adds, experimental new features that would be difficult to do in distributed. We're very open to suggestions. The advantage to working on DistributedNext instead of distributed directly is that there's just less overhead. It's a regular package, it's not a standard library, so it's easier to get stuff merged and to play with it. And a lot of the improvements and bug fixes that we've made have already been upstream to distributed. So like these bug fixes for thread safety, for example, and like some various other bug fixes that we came across. I would also like to give a shout out to the original developers of Distributed because it is kind of an impressive library and a lot of work was put into it. And with that, I am done and would be happy to take questions. Thank you.
Hi, thank you so much for the work. The existence of a standard library distributed package was initially what brought me to Julia. The main trouble that I found with it was the performance. The architecture of it having a main head node and then everything else being remote, especially compared to things like MPI. So when you want to go distributed, you probably want to scale to hundreds or thousands of nodes. How do you do in terms of performance? I love the quality of life. It's much saner than MPI. I mean, that doesn't say much, does it? But it's the performance that in the end makes you want to use distributed.
Are you talking specifically about communication performance, like the example I gave before with the remote channels?
I suppose both communication performance and also things like collective communication, the reduction algorithms and all the things that you get from MPI.
Yeah, so in that sense, I think distributed is somewhat lower level than MPI. It doesn't support any of the collective operations in MPI, and for that sort of thing, I think you would maybe want Dagger instead. When it comes to communication performance, I think we just have to work on it to make it better. It's definitely much slower than MPI right now. Like you saw, it took, I think it was like 60 milliseconds or something to transfer one number, one integer from one processor to another. There's something going on there. Right, so so the conclusion would be, it's probably quite lacking compared to MPI when it comes to communication.
My question is more related to the architecture. Sure, you can build higher level tools like reductions and collective communication on top of what you've made in distributed. Is there anything in the architecture of distributed that would make it not scale as well as MPI? I remember a while ago I asked Valentin Shoravi about distributed, and he said that he had some experiments where communication was able to be faster than an MPI because you can serialize while communicating, which is something that, or
sure,
I think I'm remembering that correctly.
We also have a potential answer from the audience.
Go for it. Yeah.
So really the architectural issue of distributed is the 1 to n issue. MPI does somewhat have that issue because you do still have rank 0 doing quite a lot of stuff, doing a lot of setup. There are a variety of solutions. I don't think changing that architecture would necessarily work out very well. We still, frequently people are starting up distributed workers from their laptop, from a REPL. You already have a REPL running, and then you just add procs. Like that is, I think that provides a very nice interface. I don't know if we'd want to change that, but I do think there is the chance for optimizations, doing things like for example, one of the bottlenecks for distributed is just like starting up 100,000 workers because you need to start one and start the other, just communicate some stuff, and that takes linear time, which is not great. You can implement optimizations though that say starts up 4 workers and then 4 workers starts up 64 workers, et cetera, et cetera. I just think no one has really gotten around to implementing those, but there has definitely been talk that is something that we can do to get around a lot of these issues, to bring loading or to bring startup time down from insane levels down to manageable levels. And there's a lot of optimizations that we can apply that just have not yet been applied, that still allow us to have this architecture and also scale to MPI level numbers.
But it's possible, and it's something that you want to do.
Yeah, I mean, people have done it before. You can ask Viral Shah at Julia Hub. I know he's done quite a lot with distributed. He was one of the original maintainers back years ago. He and many people at Julia Hub have pushed distributed to levels like that, and I'm sure they have war stories. So I would ask them how that went. But it is something we're interested in working on, absolutely.
It would be amazing to have the performance of MPI and the usability of distributed. And being able to use a REPL, have an interactive session, while having MPI workers.
Right, and just to repeat, it would be great to have essentially the power, the power and scaling of MPI, but with the conveniences of distributed. And yeah, completely agreed. And I think that's really what we're driving towards. I mean, we're looking at HPC use cases and thinking like, how can we meet the existing HPC ecosystem with distributed?
That was the original hope of distributed.
Absolutely, yeah. It just
And then people sort of gave up after a while, and it's wonderful to see people like yourself coming back and doing it again.
Yep.
I'm going to shamelessly add my own opinion at this point and say there are so many applications using MPI. and then you ask the user, do you want to use MPI? And I almost always hear a resounding, hell no, but it's the only thing that works and has performance at the level that we needed. So I mean, look at PGAS and things like that. We would love to use that, and then it doesn't work at scale, right? And so, anyway, this is merging with the panel, by the way, but maybe we will first, if there are any other questions specifically for James, we can ask them, otherwise we can start merging into the panel. All right, let's thank James one more time.